For thousands of years, scientists have tried to map how reality organizes itself. The search spans biology, physics, and sociology, producing thousands of theories that attempt to explain the intricate machinery of the universe. Historically, systems thinking has been treated as a loose family of insights. It is categorized as a diverse collection of methodologies, philosophies, and frameworks that share a general intuition about interconnectedness. According to theoretical scientist Derek Cabrera, this historical fragmentation is an illusion. The chaos of competing theories exists because past thinkers were observing isolated pieces of a single, highly specific reality. They saw the fragments, but lacked the equation that binds them together. Cabrera identifies this underlying reality as DSRP: distinctions, systems, relationships, and perspectives. He argues this is not a subjective model, but an immutable cognitive law, the universal software running organized complexity across all scales. If this theorem holds up to scrutiny, it provides the necessary formal structure to move systems thinking from a descriptive philosophy into an empirically testable science of organization. To test Cabrera's claim, we need to audit 2,500 years of scientific thought. We will apply his 4 variables directly against history's most significant breakthroughs to see if they map to this underlying equation. We start with the 4 core patterns that govern all organized complexity: distinctions, systems, relationships, and perspectives. Our investigative method is straightforward. We will populate these quadrants by extracting the raw cognitive logic from the key scientific shifts we've tracked since the pre-Socratics. We will trace exactly where these scientific titans succeeded and precisely where their models hit a theoretical ceiling because they were missing one or more of these 4 variables. This structural audit will determine whether the seemingly chaotic timeline of human discovery is actually the slow, piecemeal unearthing of a single architectural code. The D pattern stands for distinctions. It is the rule that every system requires boundaries. An identity is only ever constituted by defining what it is and distinguishing it from what it is not. We find the mathematical proof for this operation in the mid-20th century, during the birth of information theory. Claude Shannon mathematically formalized communication. He defined the transfer of data strictly as the reduction of uncertainty. Shannon proved that the fundamental act of communication requires choosing one specific message from a set of all possible messages. Mathematically, choosing a single signal and discarding the rest is a pure distinction operation. This cognitive pattern echoes backward through history. It is the exact same logic driving Hegel's dialectic, the act of distinguishing a thesis from its antithesis to generate new meaning. Without the D pattern, science lacks the necessary cognitive software to define boundaries. You cannot analyze a system if you lack the mechanism to define what is in and what is out. The S pattern represents systems. This is the structural organization of reality, where wholes contain parts and those parts are themselves wholes, nesting infinitely. The earliest intuition of this structural nesting belongs to Aristotle and his formal causes. Aristotle stated that the whole is something over and above its parts. This classical dictum is the first natural language articulation of the S pattern, recognizing that organization generates its own unique properties. 2,000 years later, economist Herbert Simon observed this same property in complex organizations. He defined it as nearly decomposable hierarchies, structures where local parts group into larger wholes to prevent system-wide informational overload. But the S pattern has a limit. The ancient atomists possessed the S pattern, allowing them to split matter into increasingly smaller parts. Because they lacked the other variables, their logic resulted in rigid reductionism. The S pattern provides the essential structural architecture for complexity, yet a system comprised purely of structure remains entirely static without a force to drive it. That driving force is the R pattern, relationships. This accounts for the dynamic causal loops, the action-reaction exchanges, and the relational tendencies connecting the components of any system. The entire post-war field of cybernetics, pioneered by Norbert Wiener, was built on discovering this exact variable. Wiener rehabilitated the concept of teleology, the idea that things operate toward an end goal. He proved that goal-seeking behavior is mechanically achievable through negative feedback, That is an R-pattern loop in action. Cybernetics beautifully formalized relationship mechanics. However, as an isolated discipline, it lacked an account for distinctions, structural nesting, and observer perspectives. Later, Ross Ashby introduced the law of requisite variety, proving that a system's internal flexibility must match the external complexity of its environment. It remains a brilliantly rigorous theorem concerning a purely R-pattern constraint. But a science dedicated exclusively to relationships is structurally incomplete. It maps the interactions while ignoring the boundaries containing them, or the biases of the scientists drawing the map. The P pattern stands for perspectives. It dictates that all complex systems are observer-dependent. A system is always viewed from a specific point, looking at a specific view. Heinz von Forster recognized this limitation in early cybernetics. He initiated second-order cybernetics, shifting the scientific lens from simply observing systems to observing the observer. This reflexive move elevated perspective from a subjective philosophical debate into a strict structural requirement for doing accurate science. Peter Checklin applied this requirement to the corporate world through soft systems methodology. He demonstrated that defining any organizational problem is impossible without first identifying the distinct perspectives of the stakeholders involved. The P pattern reveals that objective reality in complex systems is an illusion. Every system boundary you draw and every relationship you measure is contingent entirely upon the perspective from which you stand. What happens when a theory runs all four patterns simultaneously? We find the answer in biology with autopoiesis, the self-making system. It maintains structural organization through internal action-reaction processes. Simultaneously, it constitutes its own boundary identity, observable from its unique standpoint within the environment. Autopoiesis serves as a real-world demonstration of the universal DSRP grammar running at full fibrosity. Today, the study of complexity has shifted from historical philosophy to the massive computing power of institutions like the Santa Fe Institute. Modern science can track millions of interacting agents. We have the technology to map complex adaptive systems, self-organized criticality, and the fragile dynamics at the edge of chaos. But Cabrera offers a sharp critique of modern methodology. Mapping these intricate systems without understanding the underlying DSRP variables is like practicing astronomy without knowing about gravity. You can plot the motions of the planets with accuracy, but you cannot explain why they move. When Ilya Prigogine won the Nobel Prize for his work on dissipative structures, he proved that far from equilibrium systems spontaneously generate order out of chaos. The universe actively tends toward DSRP structured complexity. DSRP supplies the missing atomic theory. It explains the exact structural reasons why open systems inevitably produce the complex behaviors that our modern computers map. Looking back at the timeline, the irony is profound. From Heraclitus to Hegel, history's brilliant minds were all touching different parts of the same cognitive structure, meticulously describing their local section without ever seeing the whole. Even Charles Darwin's grand mechanism of natural selection is ultimately an interaction of variation, populations, and environmental constraints. DSRP provides the underlying ontological structure that makes that process intelligible. Cabrera defines DSRP as an empirically testable, formally notable cognitive law rather than a philosophical framework. This identification provides the formal foundation necessary to move systems thinking beyond shared intuition into the territory of a rigorous science. After 2,500 years of searching, humanity finally possesses the explicit equation, the logic of wholes, for how the universe organizes itself.